When you train a deep learning model, typing a command like loss.backward creates an illusion. The framework seamlessly executes the command, making it feel as though you are working with simple, multidimensional grids of data that smoothly slide through the network. In practice, that is an abstraction. A tensor is a highly orchestrated stack of instructions, bridging high-level algebraic theory, the rigid layout of physical computer memory, and the execution units of silicon hardware. To understand how machine learning actually operates, we have to trace the complete life cycle of a tensor. We will follow its path from logical memory strides through the complex string parsing of execution contraction paths, all the way down to the strict mathematical constraints of backpropagation. Treating a tensor as a simple black box works for small experiments. But at the scale of modern artificial intelligence, breaking this abstraction barrier is the only way for engineers to write hardware-aware code that avoids memory overflows and processor stalls. Before a tensor becomes code, it begins as pure mathematics. Formally, a tensor is a multilinear map, an algebraic object that maps multiple copies of vector spaces and their duals to a scalar field, maintaining strict linearity in every argument. A basic image classification model might treat a single picture as a rank 3 tensor of width, height, and color channels. But as you add batches, time sequences, and relational semantic embeddings, the operations require manipulating massive dimensions that exceed the complexity of simple matrix multiplication. But the mathematics must eventually survive the bottleneck of physical logic gates. The theoretical capability to stretch into 5th or 7th order dimensions is calculated right here on the surface of a processor like this NVIDIA GH100. There is a severe architectural gap here. Math allows for infinite, abstract dimensions, while the physical GPU is a rigid, two-dimensional plane of silicon transistors with defined pathways and fixed memory banks. The speed of an artificial intelligence model relies on how perfectly the framework can compress those infinite mathematical dimensions onto that flat silicon surface. The first step in bridging that gap is data storage. In physical memory, a 3D tensor is never a cube. It is a flat, continuous 1D array of blocks. Frameworks maintain shape using stride pointers that tell the processor how many physical blocks to skip. Swapping this metadata allows instant matrix transposing. But reshaping transposed tensors fails when logical coordinates misalign with sequential bytes, causing physical gaps and non-contiguous memory. To fix this, you must call .contiguous. This command forces the framework to allocate an entirely new block of memory and physically copy the data over, so it sits sequentially in the exact logical order requested. Understanding when a tensor is contiguous allows engineers to avoid triggering these massive hidden memory copies. Unnecessary copying consumes bandwidth and creates the first major bottleneck in tensor execution. Once the memory is laid out, the tensor equation must be executed. Modern compilers parse these multilinear maps using Einstein summation strings, or einsum, to specify which axes to multiply and which to sum over. When an einsum expression contains more than 2 tensors, the compiler has to determine the contraction path, the strict pairwise sequence in which the tensors are merged. The sequence dictates computational cost. Evaluating a matrix-matrix multiplication first generates a massive intermediate tensor. Contracting the matrix and vector first keeps the shape small, dropping floating point operations exponentially, but finding this path requires immense overhead before execution begins. Because the number of possible contraction sequences scales factorially with the number of tensors, finding the mathematically optimal path is an NP-hard problem, the holy grail of modern tensor compilers. It is often assumed that finding the path with the lowest theoretical number of math operations guarantees the fastest execution time. Empirical data proves otherwise. Researchers running the NeurIPS einsum benchmark tested hundreds of contraction paths for quantum computing circuits and model counting equations. Their findings exposed a severe flaw in how libraries currently evaluate execution paths. This scatterplot of execution time versus theoretical operations reveals an anomaly. Paths optimized for the lowest operation count often run slower. This gap is caused by skewness, like a microscopic 2x2 matrix attempting to multiply against a massive 2x1 billion matrix. Under the hood, Tensor libraries map these pairwise contractions to standard Blaze calls, optimized for square, balanced matrices. When fed severely skewed shapes, the hardware suffers from memory-bound cache bottlenecks, spending more time moving data than computing it. A naive compilation strategy optimizes the math while ignoring the hardware. That oversight results in a fatal gap between theoretical efficiency and actual execution time. Once forward execution is complete, the framework must calculate the gradients of the loss to update the model parameters. This requires running the entire computation in reverse. To calculate these partial derivatives, PyTorch uses vector Jacobian products, or VJPs. A VJP projects the gradient from the subsequent layer through the Jacobian matrix of the current layer. Applying the chain rule backward requires extracting specific tensor values saved during the forward pass. If an in-place operation overwrites the physical memory of that saved state, the backward pulse finds the data gone, and the calculation instantly fails. PyTorch explicitly blocks in-place operations on leaf variables that require gradients. The framework throws a runtime error rather than compute a mathematically invalid derivative. These framework rules are not arbitrary developer choices. They are strict physical enforcements of the chain rule's mathematical dependencies. This brings us to the physical destination for these memory blocks. The hardware layer is evolving to absorb software bottlenecks, printing architectural solutions directly into the silicon grid. Modern architectures now include features like the Tensor Memory Accelerator. Instead of using software instructions to calculate spatial offsets and padding, the hardware calculates the stride logic natively at the silicon layer, freeing the registers for raw math. Google's TPUs push this further using systolic arrays. Data streams through a 2D grid of multiply-accumulate units. As each multiplication finishes, the intermediate result is passed directly to the adjacent node on the silicon, bypassing main memory entirely. Running these interconnected operations across a cluster of server modules requires immense power. Systems are wired with optical circuit switches to keep data flowing across thousands of chips simultaneously. Billions of physical transistors rely on perfectly sequenced stride metadata and flawless contraction paths. If the software stalls, the silicon sits idle, wasting energy and time. The life cycle of a tensor is an exercise in translation, mapping an abstract multilinear map into a rigid, one-dimensional array of physical memory blocks. It requires navigating a complex contraction path, balancing theoretical efficiency against the physical reality of skewed, memory-bound bottlenecks. Finally, the tensor executes inside systolic arrays and tensor cores, carefully preserving its historical state to satisfy the requirements of the autograd backward pass. Inefficiencies compound exponentially at scale. Non-contiguous memory forces physical copies. Naive einsum paths stall caches. In-place operations shatter the graph. The engineer's ability to bridge mathematical theory, memory layout, and silicon reality sets the final performance ceiling for any AI model.